The notes, if we go to page 8, and we can complete our definitions. Right, so from radioactivity, okay, so we had our definition already of radioactivity. So the activity, A, which we've looked at in the calculations, is the number of decays per second, so that's pretty straightforward. Remember, it can also be written as dN dt. When you're doing calculus later, that'll be clear to you. A becquerel then is the unit, and it's 1 disintegration per second. So 1 becquerel is 1 per second. Okay. The law of radioactive decay, calculation, okay, it's in the tables anyhow, so A equals minus lambda times n. And then the half-life, which is linked to the decay constant, the time taken for the activity of a sample to have. Okay, or the time taken for the number of nuclei, number of undecayed nuclei. To have. The decay constant, which is the link between the half-life and, the decay constant linked to the half-life. But remember, that's your definition, which is just the formula from the tables, but it's the fraction of the nuclei to decay per second. So if the decay constant is 0.01, which is 1%, that means 1% would decay per second. No, the decay constants are much smaller than that in general. Right, if we move down to the calculations at the bottom, okay, so we now have the law of radioactive decay and the linked decay constant if we don't have the decay constant. So I'm going to mark that. We're also going to put in here a little diagram of the number of nuclei, or the activity, remember. Okay, and the time. We have our decay curve, and remember to get the half-life, we get n, half n, whatever that is, and the difference between these two times is the half-life. Okay, so it's worth having that there as well. Okay. And if we go on into the next page, okay, now demonstrating the penetrating power of alpha, beta, and gamma radiation. So you'll have looked at a clip of this, okay, and what we basically have is a source of radiation, depending on whether it is alpha, beta, or gamma. We won't be doing this experiment, I can assure you. Okay, you have a Geiger counter down here, so it's a Geiger monotube with a counter on it. Right, and here then, okay, you have, at different times, you have paper, aluminium, and lead. Okay, and the count rate is nothing with sheet of paper, aluminium sheet, and lead sheet. So alpha particles start by the paper, beta start by aluminium, and alpha raised by several centimeters of lead. Okay, so as you've seen in the clip, so that experiment, so just be able to draw it and be able to explain step by step. And we have this is basically the result here. Okay, ionization effect of nuclear radiation. Okay, so we haven't looked at this, but let's have a quick look at it. So you just have a charged gold leaf electroscope, a little bit like the Rutherford experiment, or the Rutherford's the experiment to show the photoelectric effect. Okay, you bring a radioactive source close to it, and what happens is the leaves collapse. Okay, why do they collapse? Air particles are ionized at the cap, near the cap here. These air particles get ionized plus and minus. Okay, and they neutralize the cap, because if the cap is positively charged, the minus charges will go to it and neutralize, and the leaves will collapse from there. Okay, so mark that as well. So mark the two E's. We'll get back to uses of radioisotopes. We'll get back to artificial radioactivity we've looked at already, and health hazards we'll get back to. That's it. Thanks again.